NEC Article 225 requires a main breaker or other overcurrent protective device at the point where the supply enters the garage. The main breaker or device must be rated to protect the total load of the garage. Now, regarding the NEC size requirement for the feet of the garage, the rules differ slightly depending on the number of circuits in the garage subpanel. Firstly, if the garage subpanel has no more than 2 circuits, the feeder must be sized according to the ampacity of the largest circuit plus the sum of the ampacities of the other circuits. Secondly, if the garage subpanel has more than 2 circuits, the feeder must be sized according to the maximum demand load calculated in accordance with the NEC Table 220.41b, or the sum of the ampacities of all circuits plus any additional loads connected to the feeder. In addition to these rules, the overcurrent protective device and the main feeder must be rated at least as large as the conductors in the feeder cable. It's also important to consider that if the garage is used for welding or other equipment with high surge currents, additional demand calculations may be necessary. Finally, the subpanel in the garage must be correctly sized to accommodate the number of circuits and the anticipated load. Let's delve deeper into each of these aspects to ensure a comprehensive understanding. Starting with the main breaker requirement, its primary function is to protect the entire garage electrical system from overloads and short circuits. The rating of the main breaker should be equal to or slightly higher than the calculated load of the garage, but never exceeding the ampacity of the feeder conductors. For example, if the calculated load is 40 amps, a 40 amp or 50 amp main breaker would be appropriate, assuming the feeder conductors are rated for at least the amperage. When sizing the feeder conductors for a garage with no more than 2 circuits, the calculation is straightforward. Determine the ampacity of each circuit. The largest circuit dictates the minimum feeder size. For instance, if you have a 20 amp circuit for lighting and a 30 amp circuit for a receptacle, the feeder must be sized to handle at least 30 amps plus the 20 amps from the lighting circuit, totaling 50 amps. However, since conductors are typically rated at standard ampacities, you would select the next largest standard size. If using copper conductors and following NEC Table 310.16, you likely need at least a number 6 American wire gauge copper conductor, which is typically rated for 55 amps at 75 degrees Celsius. When the garage subpanel has more than 2 circuits, determining the feeder size becomes a bit more involved because the NEC allows for demand factors to be applied. This recognizes that not all circuits will be fully loaded simultaneously. NEC Table 220.41b provides demand factors for various types of loads such as lighting, receptacles, and appliances. To use this table, you first calculate the total connected load in volt-amps for each type of load. Then apply the appropriate demand factor to each total to determine the demand load. Sum the demand loads for each load type to find the total demand load for the garage. This total demand load is then used to size the feeder conductors and the main breaker. Let's illustrate with an example. Suppose a garage has the following loads. Firstly, general lighting, totaling 1200 volt amps. Secondly, receptacle outlets totaling 3000 volt amps, and thirdly, a small heater rated at 1500 volt amps. According to NEC Table 220.41b, the demand factor for the first 3000 volt amps of receptacle load is 100% and the remainder is 50%. The demand factor for general lighting is typically 100%. The heater is considered a continuous load, so it's also taken at 100%. The demand load calculation would be as follows. Firstly, lighting 1200 volt amps times 100% equals 1200 volt amps. Secondly, receptacles 3000 volt amps times 100% equals 3000 volt amps. Thirdly, heater 1500 volt amps times 100% equals 1500 volt amps. Total demand load equals 1200 plus 3000 plus 1500, which comes to 5700 volt amps. To determine the required feeder ampacity, divide the total demand load by the supply voltage. If the garage is supplied with a 240 volt feed, the required ampacity is 5700 volt amps divided by 240 volts, resulting in 23.75 amps. In this case, you would select a feeder conductor with an ampacity of at least 23.75 amps. Again, referring to NEC Table 310.16, a number 12 American wire gauge copper conductor, rated for 25 amps at 75 degrees Celsius, would be sufficient. However, it's always advisable to use a larger conductor size to account for future load growth and to minimize voltage drop. Furthermore, the overcurrent protected device on the main feeder should be sized no larger than the ampacity of the feeder conductors. It's also crucial to consider the interrupting rating of the main breaker. The interrupting rating is the maximum short circuit current that the breaker can safely interrupt without failing. The available fault current at the garage subpanel must be less than the interrupting rating of the main breaker. This is typically determined through a fault current calculation, which takes into account the utility transformer size, the length and impedance of the feeder conductors, and other factors. If the calculated fault current exceeds the interrupting rating of the breaker, a breaker with a higher interrupting rating must be used. Now, if the garage is used for welding or other equipment with high surge currents, the standard demand factors may not be appropriate. Welding equipment, for example, can draw very high currents for short periods of time, which can significantly impact the feeder loading. In such cases, it may be necessary to perform additional demand calculations or to consult with an electrical engineer to determine the appropriate feeder size. Finally, the subpanel in the garage must be correctly sized to accommodate the number of circuits and the anticipated load. The subpanel's ampacity rating should be equal to or greater than the calculated load of the garage. The subpanel should also have enough breaker spaces to accommodate all of the required circuits, plus some spare spaces for future expansion. When selecting a subpanel, consider the available space in the garage, the ease of wiring, and the overall quality of the panel. In summary, when installing a subpanel in a detached garage, it's essential to follow all applicable NEC requirements, including the requirements for main breakers, feeder sizing, and subpanel sizing. By carefully considering these factors, you can ensure a safe and reliable electrical system for your garage. Some additional points to consider include firstly, grounding and bonding. The garage subpanel must be properly grounded and bonded to the grounding electrode system. This ensures that any fault currents will safely return to the source, tripping the overcurrent protective device and preventing electrical shock hazards. Secondly, wiring methods. The wiring methods used in the garage must comply with the NEC. Common wiring methods include rigid metal conduit, electrical metallic tubing, and non-metallic sheath cable. The choice of wiring method will depend on the specific application and local codes. Thirdly, GFCI protection. Ground fault circuit interrupter protection is required for receptacles in garages. GFCI protection helps to prevent electrical shock hazards by detecting small ground faults and quickly interrupting the circuit. Fourthly, arc fault circuit interrupter protection. Arc fault circuit interrupter protection is now required for many circuits in dwelling units, including some circuits in garages. ASIs help to prevent electrical fires by detecting arc faults and quickly interrupting the circuit. And fifthly, surge protection. Surge protection can help to protect sensitive electronic equipment in the garage from voltage surges. Surge protection devices should be installed at the main panel and at the subpanel in the garage. Remember to always consult with a qualified electrician to ensure that your garage electrical system is installed safely and in compliance with all applicable codes. Electrical work can be dangerous, and it's always best to leave it to the professionals. Let's consider some examples to further illustrate these concepts. Suppose you are installing a subpanel in a detached garage that will be used for woodworking. The garage will have the following loads. Firstly, general lighting totaling 600 volt amps. Secondly, receptacle outlets totaling 2000 volt amps. And thirdly, a 1.5 horsepower motor for a table saw. The motor is rated at 12 amps at 240 volts, which equates to 2880 volt amps. To determine the feeder size, we first need to calculate the total demand load. For lighting, we use a demand factor of 100%, so the demand load is 600 volt amps. For receptacles, we use a demand factor of 100% for the first 3000 volt amps, so the demand load is 2000 volt amps. For the motor, we need to use the NEC table 430.248 to determine the full load current. A 1.5 horsepower motor at 240 volts has a full load current of 10 amps. We then multiply this by 125% as required by NEC 430.22 to account for the motor's starting current. This gives us 12.5 amps. Multiplying this by 240 volts gives us 3000 volt amps. The total demand load is therefore 600 plus 2000 plus 3000 equals 5600 volt amps. Dividing this by 240 volts gives us a required ampacity of 23.33 amps. Therefore, we would need to select a feeder conductor with an ampacity of at least 23.33 amps. In this case, a number 12 American wire gauge copper conductor rated for 25 amps at 75 degrees Celsius would be sufficient. We would also need to select a main breaker with a rating of at least 25 amps. Now, let's consider another example. Suppose you are installing a subpanel in a detached garage that will be used for charging an electric vehicle. The EV charger requires a 50 amp circuit at 240 volts, which equates to 12,000 volt amps. The garage will also have general lighting totaling 300 volt amps and receptacle outlets totaling 1000 volt amps. To determine the feeder size, we first need to calculate the total demand load. For lighting, we use a demand factor of 100%, so the demand load is 300 volt amps. For receptacles, we use a demand factor of 100% for the first 3000 volt amps, so the demand load is 1000 volt amps. For the EV charger, we need to use a demand factor of 100% as required by NEC 625.22, since this is considered a continuous load. This gives us 12,000 volt amps. The total demand load is therefore 300 plus 1000 plus 12,000, which comes to 13,300 volt amps. Dividing this by 240 volts gives us a required ampacity of 55.42 amps. Therefore, we would need to select a feeder conductor with an ampacity of at least 55.42 amps. In this case, a number 6 American wire gauge copper conductor rated for 55 amps at 75 degrees Celsius would not be sufficient. We would need to use a number 4 American wire gauge copper conductor, which is rated for 70 amps at 75 degrees Celsius. We would also need to select a main breaker with a rating of at least 60 amps, since the next standard size above 55.42 amps is 60 amps. These examples illustrate the importance of carefully calculating the demand load and selecting the appropriate feeder conductors and main breaker. Failure to do so can result in overloaded circuits, trip breakers, and even electrical fires. Finally, always remember to consult with a qualified electrician to ensure that your garage electrical system is installed safely and in compliance with all applicable codes.